All right, let's dive into one of the most important algorithms in all of computer vision, YOLO. It's a total game changer for how computers see the world in real time, and by the end of this, you're going to understand exactly how it pulls off its magic.
But first, think about this for a second. Picture a busy street. You've got cars, people, traffic lights, signs. A self-driving car has to see and understand all of that instantly. How in the world does it process that whole chaotic scene in a single moment? Well, that's the exact problem YOLO was born to solve.
So what is YOLO? It's got a great name, right? It stands for You Only Look Once. It's this hugely popular algorithm that just completely shook up object detection by finding that perfect sweet spot between being crazy fast and surprisingly accurate. And this isn't just some theory stuck in a research paper. No way! YOLO is out there, in the real world, right now. It's the engine behind stuff like video surveillance systems, those self-driving cars we just talked about, and even the face detection tech that's become so common. Its fingerprints are everywhere. Now, to really get why YOLO is such a big deal, you have to understand the old trade-off. For a long time, you had to pick your poison. Did you want a model that was super accurate but slow as molasses, or a really fast one that, made a bunch of mistakes? YOLO just shattered that compromise. It found this incredible sweet spot, delivering amazing performance by being both fast and accurate.
So how did it pull that off? Well, that brings us to the core innovation, and it's right there in the name, the one-look revolution. It's a fundamentally different way of even thinking about the problem.
See, the older methods were just inefficient. They'd look at an image over and over again. First, they'd propose a bunch of different regions where an object might be, and then they'd run a separate classifier on every single one of those regions. It was slow and clunky. YOLO just throws all of that out the window. It looks at the entire image exactly one time, doing everything, detection and classification, all at once.
Okay, so how does that single look actually turn into a full picture? The secret sauce is a surprisingly simple and really elegant idea. The grid. This is where we get into the real nuts and bolts of how this thing works. It's really just a three-step dance. First, YOLO grabs the image and slaps a grid over it. Let's say a 7x7 grid. Then, and this is the key part, each and every cell in that grid becomes responsible for making its own little predictions. And finally, the algorithm takes all of these tiny local predictions and stitches them together into one final coherent output.
Let's double-click on that second step, because honestly, this is where all the magic is happening. Every single one of those little squares in the grid acts like its own tiny detector, trying to figure out what, if anything, is inside of it.
So what is each cell spitting out? It's basically three things. First, it predicts one or more bounding boxes, the rectangle's location and its size. Second, it gives a confidence score for each of those boxes, which is the model saying, I'm this sure there's actually an object in here. And third, it gives a list of class probabilities, like, okay, there's an 80% chance this is a car, 5% it's a dog, and so on. In that original paper, it was a 7x7 grid, and each cell predicted 2 boxes and 20 different classes.
Okay, quick detour, but this is super important. Intersection over union, or IOU. It's just a simple score that tells you how much 2 boxes overlap. You just take the area where they intersect and divide it by the total area they both cover. A score of 1 means they're a perfect match. This little number is absolutely critical for training the model.
So we know what YOLO predicts, but how does it learn to make good predictions? This is another stroke of genius. Instead of some complex multi-stage pipeline, YOLO reframes the whole task as a single regression problem. In other words, it's just trying to learn how to predict the right set of numbers for any given image, the coordinates, the sizes, and the probabilities.
But right, if it's just predicting a bunch of numbers, how does it learn from its mistakes and actually get better over time? Well, the answer is all about how we measure its errors when we're training it.
So here's a really clever detail. For any real object in an image, the model's going to make a bunch of different box predictions. To figure out the error, we only pick one of them to be responsible. And we pick the one that has the highest IOU, the best overlap with the real object. All the other predictions for that object just get ignored for that training step.
The model's performance is all measured using something called a loss function. You can just think of it as a penalty score. The bigger the gap between what the model predicted and what the actual truth is, the higher the loss, the bigger the penalty. The entire goal of training is to just get that score as low as possible.
And YOLO's loss function really has 2 main ingredients. You've got the class loss, which is the penalty for getting the object's identity wrong, calling a cat a dog. And then you have the localization loss, which is the penalty for messing up the bounding box.
And we can slice up that localization loss even more. It's made of 2 parts, a coordinate loss,
for being wrong about the box's position or size, and a confidence loss, for being wrong about whether an object was even there to begin with.
Now look, the first version of YOLO wasn't perfect. I mean, no version 1 ever is, right? It had some very real limitations, but what's so fascinating is looking at the clever, practical hacks the creators came up with to get around them.
So here were the big headaches. Each grid cell could only predict one type of object, so if you had a person walking a dog in the same cell, it would get confused. It also had a hard time with clusters of small things, like a flock of birds. And one of the weirdest problems was that a small error in a tiny little box was penalized just as much as a small error in a huge box, which just doesn't feel right.
So what'd they do? Well, for that box size problem, they did something that sounds a little weird, but is actually brilliant. Instead of having the model predict the width and heights directly, it learns to predict their square roots. It's this clever little math trick that basically makes errors on small boxes feel more important, and it really helps stabilize the whole learning process.
But that still leaves the biggest issue, the elephant in the room, really. In almost any picture, the vast majority of those grid cells are just empty background. There's no object in them. And during training, this would just totally overwhelm the model and push all its confidence scores down to 0. So how do you fix that massive imbalance?
The solution? They use scaling factors. It's like they put a couple of volume knobs on their loss function. They set a parameter called lambda coord to 5, which basically screamed at the model, hey, getting the box coordinates right is 5 times more important. And then they set another one, lambda no obj, to 0.5, which whispered, don't worry so much about the empty cells, they're only half as important. It was simple and unbelievably effective.
And that really brings us back to the heart of it all. The real power of YOLO comes from its elegance and its simplicity. By taking this incredibly complex computer vision task and boiling it down to a single regression problem, they created this unified, fast, and powerful architecture that totally changed the game.
It's kind of wild to think that the original YOLO paper came out way back in 2016, and the technology has just gotten exponentially better and faster since then. So that leaves us with this huge, fascinating question. Now that we've finally given computers the ability to see and understand our world in real time, what are we going to build with it next?